Let's solve number 19 on the 12B, number 23 on the 10B. Let's see how we can tackle this problem. We have a rectangular grid of squares, 141 rows and 91 columns as I have drawn over here. Each square has two numbers, one from Horace and one from Vera. And I'm going to use purple and orange to denote them throughout this solution, just to be clear here. Okay, so Horace and Vera, they each put numbers from 1 to 141 times 91 into the squares. Horace would fill it horizontally, so 1 to 91 in the row 1. Okay, what does that mean? Let's see here with Horace. So we would have, let's say, 1, 2, all the way till 91. And then next number, row number 2, 92 to 182. So 93, 182. Okay, row 4, 183, 184, all the way till 273, and so on. I'm not going to draw the rest. And then Vera is filling the grid vertically. So Vera would be doing 1 to 141. So Vera is 1 to 141 in the order from top to bottom in column 1. So 1, 2, 3, 4, or not 4. That would be like 140, 141. And then after that, we'd go to the next column. And then we would have, okay, 142, 143, 144. And then this would be 281, 282, and so on. We would continue doing that same pattern. And we're asked to find how many squares get 2 copies of the exact same number. So obviously doing this by brute force is going to be near impossible. So let's write expressions for Horace's number and Vera's number in each square. Okay, so Horace's number, let's try and figure it out what it's going to be in terms of our row and column. So let's say we have a row number. Let's say our row number is R, right? R, let's say. And let's say our column number, let's say that is C. So we're going to try and find an expression for Horace's number and Vera's number in terms of both R and C. So we're going to use R and C to come up with an expression for Horace's number and Vera's number. Okay, so Horace's number, let's start off with that. We have something filled in here, that's also already nice. So as you can see, 1 to 91 is here. So clearly it's gonna, whatever the column is, so in the first row, it just depends on the column number. In the first row, then we just have our value C. In the second row, okay, now we have, it's like 91 plus column number, right? So let's say column number was 2. So now we're adding 91 because we're in the second row. Okay, and then third row. Now we're adding 182 because we're in the third row. So it seems like we always have this column number by default, right? We have 1 to 91. And then depending on which row we're in, we're going to be adding an additional multiple of 91 depending on how many extra rows there are, right? So let's say we're in the first row, then this quantity is 0. So then it's just literally going to be the column number. But let's say we're in the second row. Now we're going to have to add 91 to the column number because 1 to 91. Now we're in the second row. So now we're increasing the number by 91 each. So 91 plus 91 plus 91. Okay, so now we see this will continue till the very end. So Horace's numbers is going to follow this exact expression. And Vera's numbers is going to be very similar here. So Vera's numbers, let's say, is column, so it's almost the entirely same logic. Okay, so Vera's number 1 to 141. Clearly, it will depend on the row number. So whatever the row number is, that's going to be like its kind of baseline value. And then we're going to increase it by 141, right? Each time we finish this 141, for how many each extra column we have. So if we have one extra column, for example, in column number 2, we'll be adding 141 to our baseline row value. This is our baseline row value because we're in the second column. We add 141 to each of these terms. So now we have expressions for Horace and Vera's number. And we need to find how many squares get copies of the same number. So when are these quantities equal? And now we just get an equation to solve, except note that it's a Diophantine equation. So we know that both R and C are integers, right? 141C minus 141. Let's subtract R and C from both sides. So we get 90R minus 91 equals 140C, 140C, right? Because we're subtracting R and C from both sides. R plus C from both sides of the equation. 140C minus 141. We can add 141 to both sides. We will get plus 50 over here. Then divide by 10 to both sides. So 9R plus 5 equals 14C. Okay, and now all we have to do is figure out what values of R and C such that this actually works. So now you might, how do you actually approach this? 9R plus 5, 14C, you might notice, okay, when it's 1, 1, it immediately works, right? That's something you might notice right off the bat. And that makes sense. We both start at 1 in this square. And then so that's like a nice thing that we saw immediately. How do we know what values of C will produce this? Well, here's a really neat trick. Imagine we take this whole equation mod 9. Why 9? Because then this will go away. But we would get that 5 is congruent to 14C is the same as 5C mod 9. So 5 is congruent to 5C mod 9. And we can divide by 5 from both sides. The reason is because 5 is relatively prime to 9. So we're good here. And we get that 1 is equal to C mod 9, or we'll just say C is 1 mod 9. So whenever C is 1 mod, so the reason we do this, let me actually clarify a little bit here. The reason we do this is we need 14C minus 5 to be a multiple of 9. And this will happen, 14C minus 5 will be a multiple of 9 whenever 5C minus 5 is a multiple of 9, or 5C is the same as 5 mod 9. So whenever we have C is 1 mod 9, we have that this quantity will be a multiple of 9, and then we get an integer value for R. Let's see what values of C could actually work here. So we'll move that to the side. We know C has to be 1 mod 9. So let's say C equals 1. Now clearly we get R equals 1, right? 14 minus 5, that's 9. What about C equals, well, the next value is 10, right? We get this quantity is going to be 135. So R is 15. So R is 15 over here. Now let's say our next choice maybe is a 19. And we know that we're going to get some value of R. I'm not going to calculate it from here. The question is, what is the largest value of C that could work? Well, clearly in our diagram, we know that we can't have any columns after 91. So theoretically, we should be able to go up till 91, and then that's it. And then, okay, at C equals 91, what is the value of R? So we have, okay, 14 times 91 minus 5. And, okay, let's just do that here. 910 plus 364. There's a shortcut which I'll explain in just a moment. And then we subtract 5, so we get 1269. And now we just divide this by 9 to get 1, and then 4, 1. And as you can see here, C equals 91, R equals 141. Notice something interesting. That's exactly this point right here, which makes perfect sense because we're both Horace and Vera end at this square. So this makes perfect sense why our last value that would work is when C equals 91 and R equals 141. So now the question is, how many different values are there in our list here? And to do that, we just use our standard formula, right? We have 91 minus 1 over 9 equals 10, right? So we're going up 10 times, right? That's how many times we go up, right? So we have 10 additional terms on top of our first one because we go up 10 times, and then as a result, we go up 90 in our column number. So we have, okay, plus 9, all the way till plus 90. So we have 10 of these values, and then we have 1 additional, right? So we have 11 total values here, and our answer is 11 for this problem. Right, so that was kind of neat how we realized that the last value is common, the first value is common, and then some other random values in between, which we found to be these points over here, which you can find using this formula here. So we found a really clever solution using the fact just writing the equation. That was the key trick here. And then noticing the Diophantine aspect of it. Noticing how this quantity had to be a multiple of 9, and that happens whenever C is 1 mod 9. That was the key trick for this problem. I hope you enjoyed.